Here's a question that should keep you up at night. What if our universe didn't begin with a bang? What if it bounced? Let's start with what we know. Around 13.8 billion years ago, according to the standard model of cosmology, everything that exists, every star, every galaxy, every atom in your body, was crushed into a single infinitely dense point. Then came the Big Bang, a violent, explosive expansion. The universe ballooned outward. It cooled. Plasma condensed into atoms. Vast clouds of hydrogen and helium drifted through absolute darkness. Over hundreds of millions of years, gravity slowly pulled those clouds inward until they ignited. And the first stars were born. Those stars clustered into galaxies. Galaxies merged into superclusters. And here we are. It's an extraordinary story. And it's backed by an extraordinary amount of evidence, from the cosmic microwave background radiation still echoing across the sky today to the redshift of distant galaxies racing away from us in every direction. This isn't a guess. This is one of the most well-supported theories in all of science, but it has a problem, a massive one. Physics absolutely despises infinity. When the mathematics of a theory spits out an answer of infinite density, infinite temperature, zero volume, that's not a result. That's a warning sign. It means your equations have broken down. It means your theory is telling you it can't handle what you're asking it to describe. And that's exactly what happens at the singularity. General relativity, Einstein's greatest achievement, our finest theory of gravity, leads mathematically inevitably to the singularity. But general relativity and quantum mechanics, our best framework for understanding the subatomic world, fundamentally cannot coexist in the same equations. They clash. The math falls apart completely. And at the moment of the Big Bang, when the universe was simultaneously at its smallest and most energetic, you desperately need both theories to work together. They don't. This crisis, this mathematical dead end, has pushed theoretical physicists toward a radical question. What if the singularity never actually happened? What if the universe didn't have a beginning in the way we normally imagine? What if, instead of starting from nothing, it bounced from something? Picture the universe as a living thing. Breathing, expanding outward like an inhale, then eventually, slowly, inevitably, contracting inward like an exhale. Here's the scenario. Imagine a universe much like ours. It expands for hundreds of billions of years, but at some point that expansion runs out of steam. Maybe the dark energy driving it decays. Maybe the total gravitational pull of all the matter in the universe finally gains the upper hand. Whatever the reason, the expansion stalls, reverses, the universe begins to collapse, slowly at first, then with gathering, terrifying momentum. Galaxies crash into each other. Solar systems are ripped to pieces. The temperature of the universe climbs as everything is squeezed closer together. The background radiation, once a faint cosmic whisper, heats up into a roar. Everything gets hotter, denser, more compressed by the second. This is called the Big Crunch. And in the conventional picture, it ends the same way it began, in a singularity. But what if it doesn't? This is where a cutting-edge framework called loop quantum cosmology enters the picture. According to this theory, space-time isn't the smooth, continuous fabric that Einstein described. At the smallest possible scales, it has a granular, pixelated structure. Space itself is made of tiny, indivisible units, quanta, or loops. And crucially, those pixels of space cannot be compressed to zero. There is a hard physical limit to how tightly you can squeeze them. So as the collapsing universe approaches that limit, as it reaches a state of almost incomprehensible quantum pressure, something extraordinary happens. The quantum structure of space-time pushes back. Gravity, which has been driving the collapse, effectively flips. It becomes repulsive. The universe cannot shrink any further. The crunch becomes a bounce. In a fraction of an instant, collapse reverses into expansion. A new universe erupts outward. According to this model, that new universe is ours. But here's where things get genuinely strange and genuinely exciting. When the old universe collapsed and bounced, was everything destroyed? Was the slate wiped completely clean? Maybe not. Recent research published in the Journal of Cosmology and Astroparticle Physics, drawing on observations from the James Webb Space Telescope, suggests that something might have survived. In the unimaginable heat and pressure of the Big Crunch, ordinary matter wouldn't last a millisecond. Stars, planets, atoms, protons, neutrons, all of it would be pulverized into a featureless, superheated primordial soup. Every structure the previous universe had ever built, obliterated without a trace. But black holes are not ordinary matter. Black holes are already the most extreme objects in the universe. Regions where gravity has overwhelmed every other force, where space-time is warped beyond recognition. And there's a specific category of black holes we need to focus on here. Primordial ones, relic black holes, objects that formed not from dying stars, but from the extreme density fluctuations in an earlier universe's history. As the previous universe contracted toward the crunch, everything around these relic black holes got denser and denser. But these objects are already essentially the densest things that can exist. According to the mathematics of the bounce model, they don't get crushed, they don't get pulverized, they just endure. They ride out the collapse, survive the bounce, and emerge on the other side, carried into our universe as passengers from a universe that no longer exists. If this is correct, our universe contains objects that are older than the universe itself. Let that sink in for a moment. Now think about the properties of these relic black holes. They are massive. They exert powerful gravitational attraction. They emit no light. They don't interact with normal matter in any detectable way, except through gravity. Massive, invisible, interacts only gravitationally. That is the exact description of dark matter. For decades, physicists have been hunting for dark matter, the mysterious invisible substance that makes up roughly 27% of the universe's total mass energy content. We know it's there because of the gravitational effects it produces. Galaxies rotate at speeds that only make sense if there's far more mass present than we can see. But despite enormous efforts, nobody has ever directly detected a dark matter particle. No experiment has caught one. No detector has registered a hit. What if we've been looking for the wrong thing entirely? What if dark matter isn't some exotic, undiscovered particle? What if it's actually a vast, invisible population of ancient black holes, survivors of a universe that collapsed before ours began? This idea is elegant precisely because it requires no new physics, no undiscovered particles, no speculative forces, just gravity, the physics we already understand, applied to objects that predate our own cosmic era. Dark matter isn't a mystery particle. It's a survivor, and there's more. Because this theory doesn't just potentially solve the dark matter problem, it might also solve one of the biggest puzzles the James Webb Space Telescope has handed us. JWST was built to peer into the earliest chapters of cosmic history, to watch the very first stars and galaxies switching on in the darkness. And it has done that, spectacularly. But it also found something nobody expected, something that sent shockwaves through the astrophysics community. Supermassive black holes, monsters with masses millions, sometimes billions of times greater than our sun, fully formed, already enormous, and sitting inside galaxies that existed just a few 100 million years after the Big Bang. This is a serious problem. Under our standard models, black holes form from the deaths of massive stars. Then they grow, slowly, by swallowing surrounding gas and dust and merging with other black holes over billions of years. To build a supermassive black hole, you need time. Enormous amounts of it. The universe simply hadn't been around long enough at that point for these objects to have grown that large through conventional processes. It's like finding a 1,000-year-old redwood tree in a garden that was planted last spring. It doesn't fit the timeline. It shouldn't be there. Astronomers have scrambled to explain it. Maybe the very first stars were extraordinarily massive, leaving behind unusually large black hole seeds. Maybe enormous clouds of primordial gas collapsed directly into black holes without ever forming stars. These are valid hypotheses, and researchers are actively pursuing them. But the bounce theory offers something more radical, and arguably more satisfying. What if those supermassive black holes didn't grow inside our universe at all? What if they arrived already fully formed, carried over from the universe that came before? If relic black holes survived the bounce, they would have entered our universe already enormous. As the new universe expanded and the primordial plasma cooled, matter would have immediately begun clumping around these massive gravitational anchors. Galaxy formation wouldn't need to wait for black holes to slowly grow. The seeds were already there, massive, ancient, ready from the very first moments of our cosmic era. This would explain exactly what JWST is seeing. Not a violation of physics, not a flaw in our models, but the gravitational fingerprints of a universe that existed before ours. One universe collapses, another is born from the wreckage, and certain things, the densest, most extreme objects in existence, make it through the transition, carrying the legacy of a dead cosmos into a living one. The Big Bang wasn't the beginning of everything. It may have been the beginning of this chapter. And before it, another universe, another story, another chapter we're only now beginning to read. What do you think? Could the universe be cycling through death and rebirth? Could dark matter be ancient black holes from a previous existence? Drop your thoughts in the comments. This conversation is just getting started. And if questions like this are the ones that excite you, subscribe to Territory, because this is your space.